Welcome to Module 202F on Power Factor Correction. This is where we're going to put all the knowledge you've gained so far into a practical use. We're going to look at power factor correction and how it affects the buildings and the supply for the building. This module is going to be split into 3 different videos. The first video is going to be based on objectives 1 and 2, where we're going to take a look at a motor circuit and find out how that circuit changes its overall dynamics when we add a capacitive load in parallel. We're also going to be looking at different ways to correct power factor in an industrial plant and why it's a value to do that. The second video is going to be based on Objective 3, where we size our capacitive load based on our power method. And our third video is based on Objective number 4, where we do similar calculations, but instead we're going to be using our currents. Let's start by looking at a typical motor and what happens to the circuit when we add a capacitor in parallel to it. This motor is drawing 23 amps and is operating at a 0.46 lagging power factor. Induction motors typically have a very low power factor because they have to create a magnetic field in order to turn the rotor. What this means for my supply is it is drawing 23 amps at a 62.6 degree lagging angle. If you look at the power values for the motor itself, you will see that it has a very high reactive power. This is what is creating that magnetic field. This also results in having a very high apparent power at 5.5 kVA. Let's look to see what happens to my overall circuit when I add a capacitor in parallel to this motor. You'll notice that even though we added something into the circuit, we have not changed anything at all when it comes to the motor. It's still drawing 23 amps and is still operating at a 0.46 lagging power factor. Nothing changed with the motor. However, by adding in an 18 amp leading capacitor, I've now offset some of that load that we have with the motor. Since my capacitor is a leading power factor and my motor is a lagging power factor, their ampacities actually oppose each other. The result is that from my supply, I'm now drawing 10.83 amps and my new angle is 12.39 degrees lagging, or 0.98 lagging power factor. It's kind of odd to think that when we add something to our circuit, our total ampacity is going to go down. But if we look at our HV chart, we can see what's really happening here. In my HV chart, I can see my motor operating at 23 amps at a negative 62.6 degrees, since it is lagging in parallel. I also see my capacitor operating at 18 amps at positive 90 degrees. What's really important is to look at the vertical aspect. Since my motor has a negative 20 vertical value, my capacitor has a positive 18 vertical value, the result is to have an overall vertical of negative 2, which means I have a much smaller phase angle that I am working with, which also means my hypotenuse on my triangle is also much smaller, which means that my total ampacity is going to be reduced. Another way to look at this is by looking at the power values of these different components. If I look at the power value of my motor, as well as my capacitor, I can see that my VAR values are exactly 180 degrees from each other. That means that the power that's being stored and released in the capacitor is actually feeding the reactive power of the motor. This means on the total aspect of it, I need to supply fewer VARs from my supply, which keeps that angle much smaller. And I can also see that my total apparent power from my supply is less than half of what my motor actually requires. We can also look at the sine waves of these 2 different types of circuit. My inductive circuit and my capacitive circuit operate 180 degrees out of phase from each other. That means when one is charging, the other one is discharging all the time. So when my capacitive circuit discharges, it's at the exact same point that my inductive circuit is starting to charge. And when my inductive circuit starts to discharge, that's the exact same point where my capacitor is charging. This results in the energy just swapping between those 2 devices, which means I need to have less for my supply in order to make things run properly. Some of the observations that we can make up to this point is that my I total, when I add a capacitor in parallel with the motor, is always going to be less than the I of the motor. That's because the capacitive current is always going to offset the motor current. We also were able to see that the total apparent power is always less than the total apparent power for the motor itself. And that's because the capacitor offsetting that reactance and therefore reducing my phase angle. Since my phase angle decreases, that means my power factor increases. Because we must remember, the closer we get to unity, then my power factor gets closer and closer to 1. And having a high power factor means that we have a low power factor angle. When it comes to industrial plants, utility companies usually have a surcharge added if your plant is operating at a poor power factor. Typically, anything less than a 0.9 power factor ends up costing you more money. The reason for this is that it costs a lot of money in infrastructure in order for power plants to upgrade all their equipment. So by making sure that your business is operating at a good power factor means that they have to invest less into their own infrastructure and therefore it costs less. The first method of correcting power factors is something that we've already looked at, and that is adding a capacitor bank into the system. One of the great advantages that we have with the capacitor bank is that it really requires no maintenance. You just set it and forget it. The trick is to make sure that they are sized correctly. Since they are typically rated in kVARs, we need to know how to calculate the kVARs of our building in order to correctly size the capacitor. The other typical method that we use for power factor correction is by using a synchronous motor. Typical induction motors have one magnetic field in the stator that turns the rotor. However, with a synchronous motor, it actually incorporates two magnetic fields, one inside the stator, but also a second one inside the rotor. And by adjusting these magnetic fields, we can actually make the synchronous motor operate at a leading power factor. So therefore, it provides us with power factor correction at the same time as doing actual physical work for us. So we can replace some of our induction motors with synchronous motors and still have that power correction value added to our circuits as well. By improving our power factor, we've already seen that we can have less line current. Less line current means that we have smaller conductors to install, which is an advantage to us since that is easier for us to install, and also means that we have less line loss, which means our overall system works more efficiently. When it comes to the industrial processes and supply lines coming to our buildings, there is a lot of loss that we have on our transmission lines. And if we can reduce the amount of current on those transmission lines, it also means that more actual power is getting used instead of wasted on those lines. The other advantage when it comes to the utilities is that the entire system will be able to handle a larger power load. Meaning if I have one building that is uncorrected, when I do the power factor correction for that building, I can actually supply two corrected buildings in instead. This is the end of part 1. Review this video as many times as you like and make sure you go through the module. Then return to Blackboard, complete the worksheet, and do the knowledge check that follows. Once you've done those two things, you can continue on to part 2.